Hello and welcome back. Today we're going to talk about Unit 3, Work, Energy, and Power. These are the 5 topics you need to understand. 1. Translational kinetic energy. 2. Work. 3. Potential energy. 4. Conservation of energy. And number 5. Power. Let's begin. First topic, translational kinetic energy. First of all, we have to figure out what is energy. The energy is a capacity or ability to cause change. Or in an easier way, the energy is the ability to do work. And unit for all type of energy is joules. Or you can just write a capitalized J when you're doing other questions. Now we already know what is energy. What is kinetic energy? The kinetic energy is an energy the object has due to its motion. Basically, if an object has a velocity or an object is moving, it definitely has kinetic energy. Some real life examples are like cars driving on a highway or a running person, etc. Now, back to the topic name. What is translational kinetic energy? It is the kinetic energy an object possesses due to its linear motion. The linear motion is basically just like an object moving on a straight line, in a straight line. So translational kinetic energy in an easier way to say is just the kinetic energy an object has when it is moving on a straight line. The equation for calculating kinetic energy is Ke. Ke represents kinetic energy is equal to 1/2 times mass, which is m, right, times velocity squared. And by the way, the kinetic energy is a scalar. So you don't need to worry about the directions when you're doing the question. And the unit for it, obviously, is joules. Let me give you a very easy sample problems. This is a horizontal ground. An object with a mass of 1 kilograms is moving forward with a velocity of 2 meters per second and asking you what is its kinetic energy. So yeah, let's just plug into the equation. Ke is equal to 1/2 times m. What is the mass of this block? It is 1, right? And times velocity squared. What is the velocity of this block? It is 2. Let's plug in it, which is 1/2 times 1 times 2 squared. We can get is 2. Don't forget your units. 2 joules. So this is its kinetic energy. How about an object also on a horizontal ground with a mass of 1 kilograms moving at a velocity of negative 2 meters per second? What is its kinetic energy? Do you remember I told you that the kinetic energy is a scalar, has no direction? So yeah, so they're supposed to be the same because they have the same mass and the magnitude of the velocity is the same. So let's see. Let's plug into the equation and let's see if they're actually equal. So Ke is equal to 1/2 times 1 kilograms because 1 is its mass times negative 2 squared. What is negative 2 squared? Is equal to 4, right? So it is basically equal to half times 1 times 4 and also it's also equal to 2 joules. So it proves that the kinetic energy is a scalar and have no directions. So you don't really need to worry about the directions when you're solving any of the problems. Alright, next topic, potential energy. First of all, we have to understand what is potential energy. Potential energy is a stored energy within an object due to its position or state. And there are 2 types of potential energy. One is gravitational potential energy, which known as Ug, and the other one is Us, which is spring potential energy. You only need to understand these 2 types in AP Physics 1. And what is gravitational potential energy? It is the energy stored in an object due to its height. For example, this is a ball. No, yeah, this is a ball and this is a ground level. Because of the ball is above the ground, which means it has gravitational potential energy. And then you may ask, what is the equation for calculating gravitational potential energy? Well, good question. UG is equal to mass, which is m, times g, the gravitational constant. It depends on which planet you're on, times h. The h is the height you are above the ground level. Next, spring potential energy, US. It is the energy stored in a spring when a spring is compressed or stretched from its unstretched form. And the unstretched form is also known as equilibrium. For example, this is a wall and there's a spring on it and you're pulling it. And the original length, or at equilibrium, the spring is this long. And because of your stretching this spring, right? Because you stretched the actual length of the spring by this much, which means it has spring potential energy. And the formula for calculating the spring potential energy is US is equal to 1/2 times K. K is the spring constant, and times K times delta X squared. Delta X is the length you stretch the spring. In this example, the delta X is this part. Let me give you some very easy sample problems. For example, this is a ball with a mass of 3 kilograms, and it is 30 meters above the ground, and asking you what is the gravitational potential energy. Oh, by the way, this is Earth. So UG is equal to m times g times h, right? So let's plug in a number. The mass of the object is 3 times what is the gravitational constant on the Earth? It is 9.8, right? So let's write 9.8 times the h above the ground level. It is 30, right? So times 30, which we can get 29.4 times 30, which I think is 882 joules. Oh, by the way, the unit for both gravitational potential energy, and spring potential energy are both joules. Yeah, this is the first simple problems, and the second one is when a spring is unstretched, its original length is 0.5 meters, and then you're stretching it, right? And then you stretch it to the length of 1 meters. And the spring constant is 5,000 newtons per meter. So calculate the spring potential energy. So first of all, let's write the equation down. US is equal to half times spring constant times delta X squared. Let's plug in a number. Half is constant, just write it down. What is a spring constant? It is 5,000 over here, right? So let's write it down, times 5,000 times delta X. What is delta X? The delta X is a length is stretched, which means in this situation, it is this part. How do we calculate this part? We calculate it by using the final length minus the original length. In this situation, is 1 meters minus 0.5 meters squared, which we can get 1 over 8 times 5,000, which is 625 joules. Alright, next topic, conservation of energy. This topic is very, very important because 90% of questions you did or you met were related to this topic or somehow related to this topic. So in a simple term, the conservation of energy is basically the initial energy you have in an object is equal to the energy the object obtains at its final state. Obviously, the object must be in a closed system, which means there's no external factors or forces like friction force or air resistance forces. So the expand form of the conservation energy equation is UG1, the initial state, the gravitational energy at the initial state plus KE1, the kinetic energy at initial state, plus US1, the spring potential energy at its initial state, is equal to UG2, the gravitational potential energy at its final state, plus KE2, the kinetic energy at its final state, and US2, the spring potential energy at its final state. Do you remember last topic I told you the equation for calculating the gravitational potential energy, spring potential energy, and kinetic energy? When we plug those equations over here to the equation of conservation of energy, we will get this very long equation. Pay attention to the subscript of each variables. The subscript of a variable means although the variable still has its original meanings, it represents different values. For example, over here h1, at initial state, the object is at the height of h1. However, at the final stage, the object may at the height at h2. So when you're doing this the question about conservation of energy, you have to pay attention to each variables because they will be different at the initial state and at the final stage. You might look at this equation and you'll be afraid. What? Will I use all these terms of energy in every single problems? No, you don't always use all the terms of energy. So the very important thing for you to do is determine which forms of energy are present in the initial and final states of the system. And the equation will change depending on what kinds of energy are actually in a problem. Let me give you some scenarios. Alright, now let me give you a scenario. This is an object with mass m, and it is moving forward at its velocity of v1, and this object is height h above the ground level, which is this surface. And then when it's sliding down, it goes at the velocity of v2. Write the equation of conservation of energy. So how do we write it? So first of all, let's determine what kind of energy it has at the initial state. Is it moving? Yes, absolutely. So it has kinetic energy at the initial state. Is it above the ground level? Absolutely, because it is h above the ground level, which means it also has gravitational potential energy, which is UG. Is it on a spring, or is it any spring in this problem? No. So there's no spring potential energy, so we don't even need to write it down. So it is equal to. Now let's figure out what kind of energy there is at the final stage. Is it above the ground level? No, it's not. It's on the ground level, which means there's no gravitational potential energy, so we don't even need to write it down. Is it moving? Absolutely, which means because it is moving at a speed of velocity of v2, so there is kinetic energy, ke2. So the initial state will be ke1. Is there any spring when it's at the final stage? No, so we don't even need to write it down. So this is a simple term of conservation of energy equation, and then when we expand it, it will be half m, the mass of the object, times initial velocity squared, v1 squared, plus m, the mass of the object, times g, times h. H is the height above the ground level, right? And it's equal to half times mass of the object times final stage of the velocity, v2 squared. So this is how you figure out or how you write the conservation of energy equation. However, if there is friction or air resistance in a problem, mechanical energy won't be conserved because it is no longer a closed system. But you may ask, what is mechanical energy? The mechanical energy, in simple terms, is basically the potential energy plus the kinetic energy. Let me give you this scenario. An object with mass m is h above the ground, and it's moving at an initial speed of v naught, and it's sliding down the slope. After it's sliding down slope, it will move along the horizontal track over here and eventually come to stop, which means there's friction, right? So how do we write the equation of conservation of energy here? It's not that bad. It's not that hard. So let's try. Is it above the ground? Absolutely. So there is gravitational potential energy here. So we can write down the equation for gravitational potential energy, which is m times g times h. Is it moving at the beginning or at initial state? Absolutely. So we can write down the equation of for the kinetic energy, which is half times mass times v naught squared. Is it on the spring? No, it's not. So we don't even need to care about the spring potential energy. So it is equal to, at the final stage over here, is it moving? No, it's not. Is it above the ground level? No, because it is on the ground level. So we don't even need to care about it. Is it on the spring? No, so it's equal to 0. How is that even possible? Because mgh is positive, and half mv squared is also positive. How do positive plus positive equal to positive? So we definitely miss something. Yes, we do miss something because it is actually equal to 0 plus the energy done by external forces like friction, air resistance, or even energy loss. Energy loss is basically like transform the mechanical energy to thermal energy, but you don't need to worry about it that much. Also, you don't need to worry about the air resistance, so you only need to worry about FF. So E, yeah, it's 0 plus E external force, external force energy. All right. Now the next topic is work. The work is a process of transferring to or from an object via force causing displacement. You don't need to worry about this definition though, but you have to understand or remember this formula for calculating the work. This is work, which represented by the capitalized W, and it is equal to the action force, F, times D. The D is not the displacement here, it is actually the distance it travels, and times cosine theta. The, and it is equal to the change of kinetic energy. Or I can expand it, writing like the final stage of kinetic energy minus the initial stage of kinetic energy. The theta is the angle, the theta over here is the angle between the force and the distance. And then I don't think you will understand this definition right now, but I can give you some example problems. For example, look over here. This is a ball traveling on a horizontal track over here, and there's a constant force with a magnitude of 10 newtons, allowing it to travel forward by a distance of 30 meters from this point to this point. And it is asking you what is the work done by the 10 newtons force. Well, I already give you the answer here, but let me explain it. This is work, right? And it is equal to F times D times cosine theta. And what is F? F is just this action force, right? Which is 10 newtons over here times D, the distance it travels. It is 30 meters, and you don't need to care about the direction over here. However, what is cosine theta? Let's figure it out. I already told you it's the angle between F and D. Let's see. This is the direction of the force, right? Because it is parallel to the surface, right? So it's pointing that way. And the distance it travels, or the displacement over here, is it is pointing that way. Because it is also traveling along the horizontal track, right? Which means these two are parallel. Which also means the angle between them is actually 0. So we can write cosine 0 degrees over here. What is cosine 0 degrees? It is 1. So which we can get, it is equal to 300 joules, or newtons, 300 joules. Joules is a unit for work, or we can write 300 newtons times meters. It is also the unit for work, but we don't use it that often. Alright, now let's look at this problem. This is still a ball rolling on a horizontal track, and there's a constant force with magnitude of 30 meters, but with an angle of 60 degrees above the horizontal ground. And this constant force allowing it to travel along the horizontal track with a distance of 30 meters, which is over here. And now it is asking you what is the work done by the F. So it's still basically still the same. So let's see what we can get. The work is equal to F times D times cosine theta. First of all, what is F? The F is just 30 degrees over here. You don't really need to worry about it right now. So let's just write it down. It's equal to 30 newtons times distance they travel is 30 meters times. Now let's see what the cosine theta is. The direction of the force is pointing that way. It is also 60 degrees above the ground surface. And the direction of displacement is like this because it starts from this position and ends at this position, which means the displacement's direction is pointing that way. What is the angle between them? It is 60 degrees, which means we can write down cosine 60 degrees over here. What is cosine 60 degrees? It's 1/2. So the answer will be 450 joules. And now let's go back to the first example. This is still a ball traveling on a horizontal track, and it is going forward with a force of 10 newtons, and it travels along the horizontal track by 30 meters. And now I'm asking you, what is the work done by the gravity? Well, we can still use that formula, obviously. Work is equal to F times D times cosine theta. What is F? The F is just the gravitational force, right? We don't know here, but well, hold on a second. We can just write down Fg over here. Times the distance it travels. The distance it travels is over here, right? It is 30 meters. Just write it down. Times cosine theta. What is cosine? What is theta? First of all, let's see. The direction of gravitational force is pointing downward. However, the displacement, the direction of displacement is from here to here, which is this way. It's pointing to the right. What is the angle between them? Oh, it is 90 degrees over here because this is horizontal and this is pointing straight down, which is 90 degrees over here. So let's write cosine 90 degrees. What is cosine 90 degrees? If you plug into your calculator, it will be 0, which means the entire thing is equal to 0. So the gravitational force actually done 0 work in this situation. And now you may ask, the work can be positive and it can also be 0. Can it be negative? Now, let's see. Look at this practice problems. Not actually practice problem, like a sample example. This is a ball with a mass of 5 kilograms, and the friction constant between the bottom of this ball and the surface is 0.2. And there's a constant force with a magnitude of 10 newtons pulling it going forward and allowing it to go forward by a distance of 30 meters over here. And now I'm asking you, what is the work done by the friction force? Well, let's see. First of all, let's write down the formula for work, obviously. Work is equal to F times D times cosine theta. What is F? The F is a friction force which is pointing that way. It is the opposite direction of the direction of motion because the direction of motion is going forward, right? So how do you figure out FF? It is just how do you figure out FF? FF is equal to Fn times mu. In this situation, because it is at equilibrium vertically, because it's not moving upward or downward, which means the normal force is just equal to Fg, which is a gravitational force, and Fg is equal to mg, which is 5 times 9.8, which we can get 49 newtons. So we already knew the Fg. Fg is equal to Fn, which is 49, right? And times the friction constant, which is over here, is 0.2, which we can get 9.8. So friction is equal to 9.8 newtons. We don't need to care about direction over here though, so let's write down 9.8 times distance it travels, which is 30 meters, times cosine theta. What is cosine theta right now? Let's see. The direction of friction force is pointing that way, right? This is FF, the direction of FF. And the direction of motion is pointing that way because it starts from this position and ends at this position, which means there's a vector pointing to the right, which means this is the distance of the motion, which is also the distance of displacement. So this is the distance of the motion. It's pointing to straight right. The friction is pointing straight left, and the direction of motion pointing straight right, which means the angle between them is 180 degrees, which we can write down cosine 180 degrees over here. If you plug in your calculator, the cosine 180 degrees will be -1, which we can get -294 newtons. Nah, joules, my bad. So it can be negative. Alright, let's do a quick summary. For the questions or the practices we done before, the first step you gotta do is find the direction of the force the question asks you. You have to pay attention to this because it can ask you different forces. For example, in this situation, this is a block on the horizontal ground, and there's applying force that pulls it forward, and then it can ask you what is the work done by the applying force, what is the work done by the gravitational force, and what is the work done by normal force. It can be different answers, right? And the second one is figure out the direction of the motion. So basically figure out where to start and where it ends. So you can draw vectors from the starting points to the ending points. And this is a direction. And the third one is find the angle between them. Usually it will be in a question. Usually it will just be the angle in a question. So yeah, but you have to be careful because sometimes it will be different. And the last step is just plugging your number. Now we arrive at our final topic, power. First of all, what is power? Power is a rate at which work is done. So basically, it's how fast you can done a work. There are, there are two formulas for calculating the power. The first one is P. The capitalized P is power, by the way. P is equal to work over time. And another formula is P is equal to F times average velocity times cosine theta. Actually, we can actually get this formula from this formula. Why? Follow me. P is equal to W over T, right? How do you remember the formula for work? The formula for work is F times distance it travels times cosine theta and over T, right? And do you know how to calculate the distance? The distance is the average speed times the time. So let's write it down. F times average speed times time times cosine theta over T. Oh, now we can cancel out T on both on the numerator and denominator, which we can get F times V times cosine theta. Alright, we're done.